Hello, my name is Luis Garcia, and I'm making this video as part of SMU's Machine Learning 2 final project. And I will be giving a brief overview on the Markov chain Monte Carlo methods. So a quick walkthrough on what we're going to be covering. First, we're going to go over a brief introduction just to know what the actual methods are going to be able to give us. Then we're going to break down that Markov chain Monte Carlo name and see why it is that it is named that way. We will then be addressing why the MCMC is actually needed, as there are other sampling methods, and we will be talking about how the MCMC is used, as in how do you initiate it. Lastly, we're just going to be going over why it works and addressing any faults that the methods do have. So the MCMC is used so that you can sample from and get an estimate of a parameter from a posterior distribution. So whereas you have a prior distribution and you have a conditional on the likelihood on that, after you actually see the data, the distribution is going to change. Now, you may know what the distribution looks like, but sampling from it can also still be difficult. So quick breakdown on the Monte Carlo and the Markov chain namesake. So Markov chains, as you may know, are sequences of states that are solely dependent on the previous state. So how you got to where you were does not matter to the Markov chains, only where you were right before the move. And so the Markov chains can also be interpreted as transition matrices, as seen in the top right diagram. And as for the Monte Carlo, that is a way for you to get the parameter estimates if you do not have enough data to get so. And so you just keep on sampling. And now how this ties into the MCMC. So the Markov chain, you actually end up making a sequence of parameters, and those parameters are going to be forming a Markov chain. So whatever value you have for the parameter, you know that value, and from it, you try to see if you would accept or reject another value. So that's how the Markov chain is still applicable to the MCMC. And as for the Monte Carlo part of it, you will be sampling these Markov chains repeatedly up until that Markov chain actually reaches a stationary distribution. And so that's how those two things tie in. So I briefly touched upon the fact that the MCMC is supposed to help us actually sample values for parameter. But why is it needed? Now, so far, we've only been sampling from one dimensions or at most two. And this is very doable for us. But as we increase the number of dimensions, our sampling becomes harder to do and more ineffective. Now, one of the reasons it becomes harder to do is because we're going to be having to calculate a normalizing constant for these distributions. But the MCMC allows us to get actual posterior distributions without the need of calculating the normalizing constant. So that's how the MCMC helps us sample easier. But why is sampling in higher dimensions more ineffective? Now, by ineffective, I'm referring to the fact that, say you have 1,000 samples, 1,000 iterations that you're trying to sample from. Now, you're not going to accept every single sample that you see. You either accept that sample or you reject it, saying it is not close enough to the distribution that we want, and so we will not be taking that sample. Now, as you increase in dimensions, the probability for you to accept a sample decreases drastically. And so you're going to have to do more iterations in order to get a good number of samples that would help you get a good understanding of what the parameter actually looks like for the population. So I've talked about how the MCMC helps, any shortcomings it addresses, but how do you actually run this? Now, I'm going to speak about the Metropolis Hastings method. There do exist other MCMC methods, one of which is a Gibbs sampler, but the Metropolis Hastings is more versatile and has less assumptions to it. Thus, that's the one I'm going to be addressing. So, the first thing you're going to want to do is pick a stationary distribution for your Markov chains that will be equal to the posterior distribution you're interested in. Secondly, you're going to want to also pick a proposed distribution for the actual distribution that you see, just so that they're similar enough. And whenever you're sampling from it, you have a higher chance of actually accepting the samples that you're getting, and they would be more likely to actually be indicative of values from that distribution that you are interested in. And so once you have those two distributions, your stationary distribution and your proposed, you simply pick a value to start at. Now, a good choice would be a value near the most dense areas of your probability distribution function. And so you would pick a value, and then from that value, you would then see another value towards the probability distribution. And if that value is in a more dense area, you will move to it. And if not, you might or you might not. But that's basically all it is. You just keep on iterating and accept or reject moving to a different spot. Now, I briefly touched upon a stationary distribution being needed, but why is it needed and how does it help us? So, the stationary distribution for a Markov chain has a property which states that no matter where it is you started, the probability of being at a state is not going to be affected. And so, what this ends up helping us do is be able to pick a state to start our MCMC in without worry that the actual stationary distribution that we're proposing will shift from that posterior distribution. And now, another thing that should be noted is that though the actual stationary distribution probabilities are not changing, the speed of convergence is going to be affected by that initial value that we are picking and also by the distributions themselves. So we should be careful whenever we're picking those values because it will affect how many times we have to iterate, and it will also affect how many samples we do end up getting from those distributions. So I talked about how one of the first steps in the MCMC is actually selecting a value for the parameter that we're interested in, and that'll be our initial value. Then from that value, we will be moving on throughout the probability density functions and choosing, yes, I want to take the sample. No, I don't want to take the sample. So it's important to select a value for the parameter that is close to the densest areas in the actual distribution that we're interested in, just because it reduces the amount of time it takes for us to get there. We're eventually going to get to the denser areas because of the nature of the actual algorithms. We're considering the fact that we're at this point and we want to move over to a point somewhere else. Knowing if we are at a less dense area, we would want to move towards a denser area. And so the probability that we do so is always going to be higher than the reverse. We're not going to be moving from a very dense area in the probability density function towards the tails. It is very likely that we will reject that move and that those samples will not be picked out. And this is thanks to the actual way that the Markov chains are constructed, where we know where we're at and we calculate the probability that we will be somewhere else. So, as I just touched about, some final closing remarks just so that it doesn't feel like I'm a blind spokesman for the MCMC. It does have some shortcomings. So even if you select a value for the parameter that is very good, it still takes time for the actual stationary distribution of the Markov chains to converge to the posterior distribution that we are interested in. And what that ends up uh, having us do is we're going to have to eliminate those first few values that were not a part of the stationary distribution already converged. And so if we sample, if we iterate over the MCMC 1,000 times, it's likely that those first 100 samples that we went over were not the distribution that we were actually concerned about. And so we're going to have to disregard that. Even though we took the time to sample them, we have to disregard them because they are part of a burn in period of the actual distributions. And there are many different ways in which you can calculate what that burn in would be. Uh, but I'm not going to be covering that here. Just want to let you all know that there are ways in which you can calculate it. And you can also calculate how long it would take you to get to the convergence of that stereo distribution that you're interested in. And so, yeah, I hope I helped clear out what the MCMC is all about and hopefully inspire some people to use it.